Hello, our users. In this video, I want to show you how to compute jackknife estimates using R. And the key idea of jackknife is you exclude one observation at a time. We call it leave one out. And then you compute the statistic on the jackknifed sample. And since you're doing this for many different jackknife samples, this creates variability in the estimate of the statistic. And then it also shows the influence of an individual data point on the statistic. So this becomes very useful for identifying unusual data points. This idea is very useful, for example, in regression diagnostics. You have something called the jackknife residuals, okay, based on similar idea. Okay. And once, the strength of jackknife is very flexible, very convenient for many types of statistic, easy to implement, to program. And once you have the jackknife estimates, you can do bias correction, you can do variance estimation, and also then do statistical inferences. Another strength is jackknife does not have any distribution assumption, so it's pretty convenient. And the challenges for jackknife include it's not very accurate for non-smooth estimators. Okay, so mostly it should be a smooth function of the mean. For example, it works well. But if it's a non-smooth estimator, then it's likely to fail. Okay. And also jackknife assume independence of the data. So if you have clustered data or grouped data, it will not work very well. And the accuracy of jackknife estimates is limited by small sample size, so it cannot really resolve the sample size issue. Okay? And of course, if you have a large data set, then the computation will become really intensive. Okay. All right, let's do the bootstrap using some different approaches. The first one is let's use the bootstrap package in R. So we load it and we create a sample from standard normal distribution with sample size 20. And we just want to add the mean. So we write a theta function, which is just return the mean of the vector x. And the jackknife function is very easy to use, the jackknife of x and theta. And this will calculate the jackknife results. And the jackknife results is a list. You can get the jackknife values. These are the leave one out means. So it calculates the mean after it includes one observation. Okay. And you can also get the standard error estimate and get the bias estimate. So these are all in this results object. Okay. And the second method I want to show you is we can do manual implementation. That means we can write our own codes without calling any R packages. So let's regenerate X vector, and the length of X is stored in N, and we again using the mean function, and we calculate the leave one out values using the S supply function from 1 to n and apply for the function theta of x minus I. So that's you delete the ith observation and then you apply function theta, which is a sample mean function on it. And you do this for all the 1 from n. And then also in Jackknife, there's a value you can calculate called the pseudo values. And there's a formula n times theta of n minus 1 times leave one out. And this will be the bias corrected estimate. Okay. And then you can calculate the standard error by using this formula. So it's square root of n minus 1 divided by n times the sum of leave one out minus the mean of leave one out. It's kind of a sample standard deviation, okay? A standard error. Okay? And then you get this jackknife bias using this formula. And then, of course, if you want to calculate the bias corrected estimator, you can just calculate the mean of the pseudo values. And the standard error estimate from the pseudo value can be calculated with this formula. And then based on this, you can calculate the lower and upper limit for the 95% confidence interval. And then you can print out the leave one out estimates, jackknife standard error, jackknife bias, and then you can print them out. And also you can print out the confidence interval, okay? So again, you can see it's easy to program jackknife method, okay? Okay, now example 3, I want to show you on more complex statistics. The sample mean is very easy. You can try on sample variance, okay? But here you get, we have a data matrix created, and then this is what it looked like. Got 2 columns, okay? And the sample size is the number of the rows. Now we write the theta function. Now it's the function which is the index and data, and then you calculate the correlation coefficient of the index and column 1 and column 2. Okay, so basically this will calculate the jackknife estimate of the correlation coefficient. Now you use the results, which is the result of jackknife 1 to n and theta and x data. That's how you apply jackknife on a data matrix. Okay, and then you can show the jack values which are bias corrected, and then you can have the standard error estimate. Okay. All right, and also another method is you can directly using the apply function for a data matrix or data frame. Okay, similar, we generate a data matrix with 2 columns, and then we can use this apply function on the matrix, which is 1 to n, and then we use it on the I think 1 here, and then the function is you calculate the correlation when you delete one observation, the ith observation, and you calculate the correlation between column 1 and column 2. Okay. And then so here you get the jackknife, and then you calculate the mean. This will be the mean of the leave one out correlation. So this will be the jackknife estimate for the correlation coefficient. And then you get the standard deviation of the jackknife estimates. Okay. So, so these are a few ways you can implement the jackknife estimate. And yeah, I think if the statistics become more complex, then I think the coding will become more complex. Okay. And I hope this is helpful. Thanks for watching.